Good morning, good afternoon, good evening, wherever you are. Thank you very much for joining us in the tinyML web talk today. This is Wei Xiao from ARM. I will be your host for today's session. So first, a big thank you goes to our tinyML talk sponsor, Edge Impulse. Edge Impulse provides a cloud-based platform for ultra-low machine learning development. It offers seamless integration from design to deployment, customer experience at scale. We also have a new sponsor join us today, Maxim Integrated. Thank you for your continuous support. So we do have additional sponsorship slots available. If you want to support our program, please contact Betty at tinyml.org. 2 weeks from now, our next tinyML talk is scheduled on Tuesday, June 18th at 8 a.m. Pacific time. Our presenters will be Yang-Xin Liu from Purdue University, who is going to introduce low-power computer vision, and John Tepson from Gray Matter Labs, who is going to talk about how to save 95% of your edge power with sparsity to enable tinyML. If you are interested in presenting in our series, please email your proposal to talks@tinyml.org. So our first speaker is Igor Fedorov from ARM Machine Learning Research. Igor will talk about sparse architecture search for CNNs on resource-constrained microcontrollers. Igor is a member of ARM Machine Learning team. His focus is neural network optimization for ARM hardware. Igor holds a PhD degree in electrical engineering at the University of California, San Diego. Igor, I'm going to hand over to you.
Good morning. Thank you for the introduction, Wei. So I'd like to start by, by introducing you to the ARM Machine Learning Research Lab. And we work on a variety of topics that generally have to do with neural network optimization for hardware. Here I have a short list of recent work that we've done. So recently we did some work to do pruning, specifically targeting LSTMs for efficient neural speech enhancement on hearing aids. We've also done work on quantization, noise robust machine learning, where we discussed ways of making neural networks robust to the kinds of noise you encounter in analog computation. We've done some work on RNN compression and efficient hardware for machine learning applications. I have the link at the top right to our lab if you want to check out some more of the research that we've been doing. So today I'm going to discuss some work that we presented at NeurIPS 2019. You can check out the full paper at the link below. And this work was done in collaboration with Ryan Adams from Princeton, as well as Matt Matina and Paul Watmo from the ARM Machine Learning Lab. So I'm going to start by motivating the work by discussing the pervasiveness and limitations of MCUs and the implications that using MCUs for inference has on the kinds of models that you can run, specifically on the limitations that are placed on the CNNs that can be run on MCUs. And after describing the problem, I'm going to propose a solution, which is to use black box multi-objective optimization to search for CNNs that can actually be run on very resource-constrained MCUs. And this optimization will be over various network optimization pieces, including architecture search, pruning, quantization, as well as elements of Lamarckian evolution and weight sharing for speeding up the search. And finally, I'll show some results. So one big motivation of this work is simply how many MCUs are out there. So we found some numbers about how many MCUs were shipped in 2019, and you can see that it's about 2 orders of magnitude more than the number of GPUs shipped the previous year. And part of the big reason why MCUs are so popular is because of how cheap they are and how low power they are. So you can see in table 1 a comparison of the cost, the power, memory, and such of various computing platforms. And as you go down the list, you see how the cost goes down, but also the amount of resources that are available goes down drastically. So there are a lot of challenges to deploying machine learning models on MCUs. You might care about power consumption, latency, but really the prohibitive factor is memory, because if your model can't fit on the device or can't or the available memory on the device isn't enough to run the model, then you really can't do anything else. The 2 big limitations are the small flash memory and the small RAM. So for example, if you take a look at the device like the Arduino Uno, it only has 2 kilobytes of flash and 2 kilobytes of RAM. At the same time, we know that CNNs are kind of the state of the art in a lot of classification tasks, and we would like to use them. But CNNs have a very large model size, which is a problem given that you want to store the CNN on a device that has a very small flash. In addition, CNNs also produce very large intermediate feature maps, which have to be stored in RAM, and that's a problem when the device has a very small RAM. So as an example, typically when we learn about CNNs, the first kind of neural network architecture that you learn about is the LaNet for classifying MNIST digits. But if you take a look at this very simple 4-layer neural network, you'll see that it occupies 420 kilobytes of flash memory, which you can see already exceeds the amount of flash on a device like the Uno. And it produces a very large intermediate activations, which can't be stored in RAM. And until very recently, there was a trend where researchers were proposing to move away from CNNs on MCUs, and they're proposing different kinds of machine learning models as alternatives. For example, pruned decision trees, which are also called, I think the name was bonsai, and compressed k-nearest neighbors. In this work, we're going to instead try to find neural networks which can be run in MCUs by framing the problem as an optimization problem. And we're going to leverage some of the recent advances in neural network design to find CNNs that satisfy the hardware constraints imposed by these MCU devices. So here I have a list of the different kinds of optimizations that we considered. One of the big ones that's very popular recently is neural architecture search. So this is basically referring to trying to automatically design the architecture of the neural network, which includes things like the depth, the width, the resolution of the intermediate feature maps, the connectivity, meaning which tensors are connected to which other tensors, and the kind of operators that are used by each node. So for example, do you use a regular convolution or a depth-wise separable convolution? Another network optimization that's quite popular in the literature is pruning, which just refers to throwing away either individual weights or entire neurons from a neural network. If you throw away individual weights, that's called random weight pruning, and throwing away neurons is channel or neuron pruning. And lastly, we considered quantization, which is basically going to also reduce the number of bits needed to store the model and the intermediate feature maps. So the way we perform this optimization is we basically take all of the variables, so all of the how deep the network is, how wide it is and such, and all the pruning hyperparameters and all of the variables you would need to train this model to prune it. And we call that capital omega. And we frame the optimization problem as a multi-objective optimization problem, which I have here on the right, with 3 objectives. So number one, we want to maximize the accuracy of this trained network on a validation set. And since we're going to be minimizing all of these objectives, I have 1 minus the validation accuracy. Secondly, we want to minimize the model size such that the model can actually fit in the flash memory on the device. And the third objective will be the maximum working memory, which is the maximum is taken over all of the layers of the neural network. And the working memory is defined to be the amount of memory needed to store the intermediate feature maps to compute the Lth layer. And just to make things simple, we have here the definitions that we actually used for the model size. So for the model size, it's going to simply be the number of parameters of the neural network. And for working memory, we tried 2 different definitions. The first definition considers the amount of bits needed to store the input and the weights for a given layer. And the second definition is the number of bits needed to store the input and the output of a given layer. Now, all of these definitions are reductive to varying degrees, but it's really a proof of concept. And the point is that our system is a black box optimization system. So you could really substitute any objective into this formulation, including something like a simulator or even a measurement of the size or working memory from the device. And one thing to point out is that since we have 3 objectives here, there isn't really a unique solution to this problem. Instead, we have a curve of solutions, or a Pareto optimality curve, which is a sort of a trade-off between the 3 different objectives. And what we want to do is we find the best possible trade-off between all 3 to satisfy our constraints. In other words, we want to find the highest accuracy model that satisfies the model size and working memory constraints. So this is just one slide about the way that we do this multi-objective optimization. You can find more details in the reference I have at the bottom of the slide. In general, when we do multi-objective optimization, we want to find the Pareto frontier of a set of objectives F1 through F capital K. And one way to do that is to somehow convert the multiple objectives into a single objective, and then just apply a single objective optimizer to solve the problem. And this is called, this process of turning multiple objectives into one objective is called scalarization. And one such scalarization is this Chebyshev scalarization, which basically considers the maximum over the objectives weighted by some weight lambda. So you can think of this as sort of, we're going to be minimizing the scalarization. So this is like minimizing the worst case. So if you minimize the worst case, then you can think that you're also minimizing each of the objectives at the same time. But the interesting thing is that we can pick different weightings, different lambda, to minimize different objectives to varying degrees. So you can think if you have 2 objectives and you weight one with a 0 and the other one with a 1, then you're minimizing only the second objective, and vice versa. And by picking any lambda in between 0 and 1, you can sort of sweep the frontier and sweep all the different sorts of combinations of weightings. The other interesting thing is that you can encode preferences about the region that you want to optimize over by changing the distribution of lambda. In our case, we actually have some a priori information about which region we want to optimize in. So if we care about deploying on a Arduino Uno, then we only care about models that have less than 2 kilobytes of flash memory. or less than 2 kilobytes of RAM. We can also encode constraints about the accuracy, right? So we also, for example, for a data set like MNIST, we may only care about models that are only 95% accurate. So we can encode all of this information in the distribution over these weightings lambda. Now in practice, we don't actually know the closed form function f. We only observe samples of this function. To give a concrete example, given a neural network specification, you don't know a priori what the accuracy of that network will be until you actually train it. So you only get to observe the samples of the function. So to get around this, we use a Bayesian model. And this is sort of as a whole called Bayesian optimization. So here's a higher level overview of the whole system. So I'm just going to walk through each of the pieces and how they fit together. So I'll start with the piece in the middle, the job scheduling. So basically, this is going to have a queue of configurations of neural networks to train and evaluate. So each of these configurations is like a description of the neural network and how to train it and how to prune it. So this scheduling system sends a job to a worker, and there are many workers that are working simultaneously. Each worker then trains the neural network and prunes it at the same time. And then after it's done, it sends that trained pruned model to the evaluation block, which can really be anything. It can be an actual piece of hardware where you run the neural network and measure its latency, for example. In our case, we evaluated the neural network using closed form sort of objectives. So we looked at like I said, the accuracy, the model size or number of parameters, and the working memory. So here I have visualized a system where we only care about the accuracy and the number of parameters. And so basically the evaluation block spits out the evaluation of the neural network that it's been given. And then you basically save these observations into a list or a bucket. And for each of these buckets, for example, for the accuracy, we develop a Bayesian model of that, of the accuracy, for example, as a function of the configuration. And then we use this Bayesian model to sort of propose the next best configuration to sample in order to minimize our objective. And that's this multi-objective Bayesian optimizer piece that I described in the previous slide. So then this optimizer sort of uses the information that it's seen in the past, all the configurations, and then proposes new configurations to sample, which gets sent to the job scheduling block, which then continues to send more jobs to the workers. Okay. So in general, this process can be quite slow because training neural networks takes a long time. So we proposed a couple of different ways of speeding up the search. There's one of the ways is to do something called network morphism, which is basically like if you have a neural network, a morphism of that network is a slightly different version of the network that's quite close. So for example, if you have a network with 4 layers, a morphism of that network could be like adding a channel to the first layer. So the network is almost the same as the previous one, but a little bit different. The reason that this sort of morphisms help in a search like this is because the new network can inherit the weights of the previous one, and you can then spend less epochs training that network because you can think that this new network is quite close. So the optimal weights are probably pretty close to the optimal weights of the one you trained before. So in our experiments, we found that using this idea of morphisms leads to a search which is 2 to 8 times faster, depending on the data set. Another way to speed up the search is basically to only sample proposals that are close to the currently best configurations that you've trained. And when you put this all together, it kind of resembles this debunked theory of evolution called Lamarckian evolution, which is like where you have this giraffe that keeps getting taller. Basically, when the giraffe stretches for leaves, it passes on that property to its offspring. And so these networks that we train, when we find good ones, basically they pass on their best traits to their offspring, and that's how we find better and better networks. So here are some just a subset of the parameters that we optimized over. This is just to give you a sense that we not only did we optimize over the architecture, for example, the number of fully connected layers or the number of convolutional layers, but we also optimized over things like the resolution of the input, the number of epochs to train for, whether or not to use batch norm, as well as hyperparameters that are specific to the pruning algorithm that we used. You can find all of the hyperparameters that we optimized over in the paper. Okay, so here's yes.
I want to ask a question here. So we have some questions from our audience.
Sure.
One question is, what devices do you consider as edge device? It's like a Raspberry Pi, Arduino, or some consumer level, more consumer level products?
Okay, that's a great question. For this work, I think when we talk about edge devices, we think of like the Arduino Uno or the microbit, which have something like I think the Uno, like I said, has 2 kilobytes of RAM, and the microbit had something like 16, I think. So that those kinds of devices. Is there anything else? Wei?
Wei's video seems to have
okay.
frozen, but one of the other questions when you look at the network mutations, do you look at random ones, or you only look at ones close to the current optimization? Do you just see if there's more than one minima or maxima in the space?
That's a great question. So that sort of gets into the different stages of the optimization, which I didn't cover, but yeah. So at the beginning, we sample completely randomly in a space, which can be quite slow, but it's sort of the optimal thing to do, because eventually you're bound to find an answer. It just might take you forever. So that's what we consider stage 1. And then in the following stages, we sort of reduce the space from which we sample. So in stage 3 of the algorithm, we only sample configurations that are close to the best known configurations.
Great, thank you.
Okay, I will continue. So here I'm going to show some results about optimizing over just 2 of the objectives. So the accuracy of the model and the model size. And we tested this algorithm on 4 different data sets: MNIST, CIFAR10 binary, which is CIFAR10, which has 10 classes, but the binarized version, meaning that the first 5 classes are grouped into one class and the last 5 into another class, as well as 2 other data sets. And the point of these plots is basically to show that the proposed approach can find models that have less parameters and higher accuracy than all of the competing methods, including things like this bonsai pruned decision trees and the compressed k-nearest neighbors, which are these non-neural models that were proposed to deal with the specific limitations of MCUs. These are the Pareto frontiers that I was referring to. Another way to sort of look at these results is by looking at each method in the literature and seeing for the accuracy reported by that method on that data set, how small is the model that we find that's at least as accurate as that method? So, for example, the top left entry of this table shows, compared to Bonsai, which is a prune decision tree method, we find a model that's more accurate than that method, which has orders of magnitude less parameters than the number of parameters used by that method. And you can see that for each of the data sets and each of the methods, we find configurations which are more accurate and have less parameters. And the last interesting thing to observe is the number of GPU days which were used to find each of the configurations. So the search can be parallelized across many GPUs. So obviously, like 1 GPU day on 4 GPUs is less real hours than 1 GPU day on 1 GPU. But sort of interesting to see how long it took the algorithm to find each of these configurations. Next, I'm going to show some results about optimizing for architectures that are accurate, that fit within 2 kilobytes of flash, and that fit within 2 kilobytes of RAM. And these two different tables cover the two different notions of working memory that I discussed. So in the top table, we compare sparse with prune decision trees using the definition of working memory that accounts for the size of the input tensor and the weight tensor. And you can see in each of the cases, for each of the data sets, we find networks that are as accurate or more as Bonsai, that both fit into the flash and the RAM of the device. And then in table 4, I have results showing that in all cases except one, we find networks that are as accurate or more accurate and fit within the constraints of the problem. And the other interesting to note is that for MNIST, we actually considered the full 10 class problem, whereas Bonsai considered only a 2 class problem. So we actually solved a more difficult problem with less resources. So here are some interesting intuitions that we were able to gather from our experiments just about neural networks in general. So there is this debate in neural networks whether you should start with a large model and prune it down, or if you should just start with a small model and train it from scratch. Like, which way is better? Which way do you get a smaller model, and which way do you get higher accuracy? So I think as of today, there's no real answer to this problem, but the nice thing is that the proposed technique can actually do both. It can actually learn either to have a large network that gets pruned down, or a smaller network that gets trained with less pruning. And here are some results showing, for example, that pruning is really an essential piece of this technique. So in subfigure A, we have the accuracy versus number of parameters for sparse with and without pruning. And you can see that pruning makes a big difference. And in subplots B and C, you see this is like each point represents a neural network that's fairly accurate on the given data set, so more than 70% accurate. And you can see on the horizontal axis is the number of connections in the network before pruning, and then on the vertical axis you have the number of connections after pruning. And there's sort of an interesting trend in these, that as the number of connections in the network gets bigger, up to a point, the number of connections after pruning actually goes down, meaning that your network is sort of getting bigger, but then you're able to prune it to a smaller network, which is interesting. But then there's sort of a point where that stops being true, and as the network gets bigger and bigger, then you're not able to prune it down any longer. That's sort of an interesting intuition that we discovered. We also conducted an ablation study to basically test out how important the components of this approach are. And this ablation study considered a budget of 250 configurations tested, and the goal was to find the most accurate model under the 2 kilobyte working memory and model size constraints. So, for example, if we exclude pruning from the search, then we're not able to find models that meet the constraints within the budget. If we use something like product scalarization instead of the multi-objective approach that I described, then we get much worse results. You could almost say like these are completely random results. Product scalarization is this approach that's actually pretty popular in the NAS literature that just considers the product of the objectives. So instead of doing this complicated weighting and Bayesian optimization, they just take the product of like the accuracy and the model size and just optimize that. So you can see we get much worse results using that approach. And lastly, we considered how Sparse performs without these morphisms. So basically, by not restricting new proposals to be random mutations of old proposals, we do get networks that are more accurate, but the amount of time it takes to find networks that meet the constraint is much longer. So you can see the number of GPU days in that case is 3 versus 2 in the configuration where we use morphisms. So some last results are we did actually deploy these models on an Arduino Uno. Sorry, I misspoke. On a STM MCU, and we measured the latency, the power drawn, the working memory used, and the model size. So here the working memory is like the actual working memory used by the device, not our closed form sort of analytic expression for the working memory. And this was just meant to sort of confirm that our approximation of the working memory is good. So you can see that compared to Banzai, our approaches draw much more power and are much slower. So I think that there's something to be said for that method, and maybe we need to do more research about how to make these models faster and draw less power. But one thing to note is that other researchers have tried to do this using other methods, not architecture search, but sort of different kernels or different implementations of convolutions that use less memory. And those approaches were also quite slow in terms of latency. It's about a factor of 2 slower than Sparse on the MNIST dataset.
So Igor, we have a question here. Are the models you are using floating point models or int models?
They're quantized to 8 bits.
Thank you.
Okay, so just to conclude, MCUs are ubiquitous, but they've been largely ignored by machine learning researchers. And in this work, we tried to specifically target these resource-constrained devices because they're so important for IoT products and use cases. And contrary to much of the earlier literature, we showed that it is possible to find neural networks that can be run on MCUs with as little as 2 kilobytes of RAM. And we'd like to thank Michael Bartling, Patrick Hansen, and Neil Tan for help in model deployment. Thank you.
Okay, some questions from our audience. First one, how did you measure the power? Is it MCU only or complete system, which means MCU plus memory?
So the way we measured it was we had a little a development board, and we actually have like a power meter that connects between the power source and the development board, and we basically just read the numbers off of there. while running inferences on the development board. So I'm not sure. Does that answer the question?
Okay, let us know if you have further questions on this. The other question from our audience is your framework available online? How extensible is it for new optimization targets?
We haven't open sourced the implementation, but I think one could take the paper and implement it. It's not really that involved, and I think it's quite extensible into other objectives. You know, if you care about latency, I think you could optimize for that. Yeah.
Okay. So do you have any plots of your optimization metric versus GPU metrics?
I'm not sure I understand that question.
Plots of the optimization metric versus GPU days.
Oh, oh, you mean like how the frontier moves the longer you train for, something like that? Is that the question? I'm not sure I have those plots, but yeah, that would be interesting to look at.
Okay, yeah. So Chris, if you have a further question here, just tap in the Q&A session. So the other question, can you comment about the potential in your view of using pruning? Oh, sorry, we're getting a lot of questions. In combination with extreme quantization.
I see.
Going beyond 8-bit, or 2, or even 1-bit.
Right. Yeah, I think that is quite interesting. In this work, we only considered 8 bits, which in the context of such small models is pretty much equivalent to floating points. So yeah, we weren't really limited by the bit width. I think it would be very interesting to consider the interaction between pruning and quantization, and there is already some work in the literature about that. Part of the problem is also that it would be with modern like kernels and such, like you can't really deploy a 3-bit model right on an MCU. You would need specialized software or specialized hardware to take advantage of that. So we wanted to sort of consider models that could be deployed with standard tools and actually observed to have some benefits.
Okay, thank you. In observation of time, probably just one final question. When you talk about quantization, do you refer to post-training quantization or pre-training quantization? I guess it's
training, with training, yeah.
Yeah, during training. Huh?
Mm-hmm.
Okay. So we will not be able to address all the questions here. Please go to our forum, or we will help you answer your questions on our tinyML forum. On the screen, you can see a pop-up where we want to conduct a survey of our tinyML talks. If you can spend 1 minute to help us fill your answers, that will help us improve our future talk. Thank you very much. Thank you again for our sponsors, Edge Impulse and Maximum Integrated. So tinyML for all developers. This is the Edge Impulse 2 we have talked about. They actually offer trial account for developers to play with. And if you go to Edge Impulse, you can register an account and test out your tinyML solutions on Arduino device, STM device, or even use a WebAssembly interface to test it on your mobile phones. It provides a seamless developer journey, and it becomes one of my favorite tools. Again, next tinyML session is actually scheduled on next Tuesday, June 16th. Sorry, I messed up the date earlier. Our presenter will be Yang-Xin Lu from Purdue University and John Tepson from Gray Matter Labs. It will be at 8 a.m. Pacific time. If you want to participate in our tinyML web talk, please submit your proposal to talks@tinyml.org. So again, thank you very much for your participation today. Looking forward to seeing you next week.